You know, we tap on apps on our phones dozens, maybe hundreds of times a day. But have you ever really stopped to think about the incredible journey that brought it to your screen? Well, today we're going to pull back that curtain and see exactly how software is made.
It really is a fascinating journey. It all starts with just a spark of an idea, right? And it ends with this powerful tool right in the palm of your hand. So let's follow that path, step by step.
And that quote really nails it. See, just like an architect needs a blueprint, a programmer needs a solid plan. In fact, long before anyone writes a single line of code, the most important work has already begun.
Okay, so let's dive right into this first stage. This is where we take that initial idea and map out exactly what our program needs to do. And I mean down to the smallest detail.
To build this blueprint, programmers usually have two go-to tools. On one hand, you've got pseudocode. Think of it kind of like a recipe, just written out in plain English. And on the other, you have flowcharts, which are basically visual maps that show every single turn and decision the program will make.
And what's so cool about pseudocode is how simple it is. It strips away all the complicated programming language rules and just focuses on the pure logic. This means anyone, and I mean anyone, the project manager, the designer, can look at the plan and get exactly what's being built, even if they've never coded in their life.
All right, so once that blueprint is solid, it's time to turn the plan into actual instructions a computer can understand. This is where the real coding part begins.
And this is what it looks like out in the wild. This is code. It's a language of incredibly precise commands written in something like Python or C++ or Java, and it tells the computer exactly what to do. No room for interpretation.
And this is where you really see how precise programming has to be. Every single comma, every bracket, every word has to follow the language's strict grammatical rules. We call that syntax. Get one semicolon in the wrong place, and the whole program can just come to a screeching halt.
But here's a little secret about all this. Computers don't actually understand Python or C++. Not directly, anyway. They speak a much more basic language.
You see, the code we write is really for other humans to read and understand. For the machine to get it, that code has to be translated into the only language it truly speaks, machine code. We're talking just ones and zeros.
So how does our code get translated? Well, that job belongs to some special programs, and there are two main ways to do it: using something called a compiler or using an interpreter. They both get to the same finish line, but they take completely different routes to get there.
Here's an easy way to think about it. A compiler is like someone who translates an entire book into another language all at once, and then just hands you the finished copy. An interpreter, on the other hand, is more like a live translator, whispering the translation to you sentence by sentence as you go.
Okay, so now our instructions are in a language the computer can finally understand. So let's crack open the case and see what's actually happening inside the machine.
It turns out every single program, and I don't care if it's a simple calculator or the most complex video game, it follows the same fundamental three-step dance. It takes some information in, that's the input, it does something with it, that's the processing, and it spits out a result, that's the output. Input, processing, output.
And to actually pull off this dance, the software needs help from the computer's physical parts, the hardware. Each piece of hardware has a really important job to do.
First up, you've got the CPU, the undisputed brain of the whole operation. This is where that processing part happens. It takes our instructions and does all the heavy lifting, all the number crunching, all the calculations.
Now, while the CPU is working its magic, it needs a temporary place to hold all the data it's juggling. That's RAM. Think of it as the computer's short-term memory. It is super fast, but it's also volatile, which is a fancy way of saying as soon as you turn the power off, poof, everything on it disappears.
Finally, the result, the output, gets shown on your screen. And if we want to keep it around, it gets saved to long-term storage, like a hard drive. That's where it stays safe and sound, even after you shut the computer down. Now, of course, this whole journey from an idea to a working app is, well, it's rarely perfect on the first try. And that brings us to the inevitable, sometimes frustrating reality of programming: bugs. These errors usually come in two main flavors. First, you've got your syntax errors. Those are basically just typos or grammar mistakes that stop the program from even running. But then you have the much sneakier logical errors. This is where the code runs perfectly fine, but it gives you the wrong answer because the original thinking, the plan itself, was flawed.
And this is exactly why creating software isn't something you just do once and then walk away from. Nope. It's a continuous loop called the program development cycle. It's this constant process of understanding, planning, coding, testing, fixing, and then doing it all over again to maintain and improve the program over time.
So just think about this for a second. This entire incredible journey, from a simple idea, to a plan, to code, to translation, and finally to execution by the hardware, all of that is happening billions of times, every single second, inside the devices you use every day. It's kind of mind-blowing, right? Every single app on your phone, every website you visit, every piece of software you use started out as nothing more than an idea. And now you know the incredible, logical journey it took to come to life. So that leaves just one question. What problem are you going to solve next?